Okay, previously, we already learned about the regression. What is the concept of the regression and how to deal the split about the training and the testing data set. And we can see the performance. So the performance means we can see the error and we can see the R square. Now, I'm going to discuss how if we want to improve performance improvement. Before this one, let me now let's see how we can improve the performance of the regression. To improve the machine learning performance, there are some more techniques. We can use holdout method, we can use cross validation method, and we can use the grid search cross validation. Or sometimes people use the literature's name like adaptive parameter. And also we will learn how to streamline the machine learning flow. We can apply one of the tools in the sklearn. We call it pipeline. Now let's take a look one by one. Oh, by the way, I updated the presentation material. Please take a look on the new version. Holdout method. So what is the meaning by the holdout method? It is the fundamental validation technique in machine learning used to evaluate the performance of the predictive model. It is to see the performance. So the performance, it means we want to see on the new data or we want to see on the unseen data. Unseen. It means the data we have not seen before, or this is a new data. That's why we need to put into the testing dataset. Or in order to improve the performance, we need to look at the realistic scheme. Okay, the realistic scheme. It means when you try to apply the regression, when you try to apply the machine learning, it means you need to show the performance, showing the performance not on the same data. You have the training data set, accept data. So you have the training data set for building the model. It means the model or something to predict the new data cannot be used to measure the performance. So it is realistic because in the real world scenario, you will see, you will predict something that you never know before. You will predict something that is new. You will predict something that people do not know before. And we call this is the realistic scheme. And this kind of performance improvement with the holdout method, we say that it is for the unbiased estimate. Unbiased means we want to split the training and the testing. So the two data set is totally different. Because they are totally different, then it is for the generalization. So we can make a model, then the model can be generalized. It can be applied to any data set. It can be applied to new data set. And also it is to improve the reliability. See, that's all. So when we use the holdout method, this is the definition. This is the fundamental validation technique. Usually we will split, as we already learned last time, we took 80-20. It means 80% will be for the training data set and 20% will be for the testing dataset. So we have the overall dataset. Now you already submitted your proposal for the team project. Now let's suppose you have 1,000 data. So from 1,000 data, 80% from the data you will apply it for the training dataset. So this data you will build the model. After you have the model, and you will pass it into the remaining 20% or the 200 data. So those 200 data will be used to check whether the model is good or not. Sometimes we can use 70-30. If we use 70-30 means 70% will be for the training data and 30% will be for the testing. On some cases, you need 60-40. It means 60% it will be for training data and the 40% it will be for the testing. Now the question is, when we need to use 80-20? When do we need to use 70-30? When do we need to use 60-40? So if the data is small, it is good to use 60-40. Let's say I have only 10 data sets. Maybe you will have question, why we have very small data set? Yeah, the data set, it is very difficult to get the data. For example, you want to get the data from the nuclear accident. Do you know nuclear accident? Hexagon. So the nuclear accident is very rare. So you cannot get the data frequently. So the data, because it is too small, you can split into 60-40. Then we can have a good proportion, 6 data for the training, 4 data for the testing. But if you have a lot of data, you can use this 80-20. For example, you have 1 million data. Then you will put 800,000 data for the training and the remaining 200,000 for the testing. So it is good enough for checking performance. In some cases, people split into 3 distinct sets. We call it, this is the training data set. And then we have a validation data set. And we have a testing data set. So in the training data set, we will do the modeling. So we will build the model with the training data set. After we build the model, we do the validation with this data set. After we do the validation, after we know that, okay, the performance of the model is good on this data set, then we will apply to the training data set. So it means there will be 2 steps for checking the model. So the proportion can be different. Maybe in this case, you have 80-20. From the 80%, you allocate the 60% for the training and 20% for the validation. Sometimes you can also use like 80-20. And from this one, you put 90% of it and 10% of it into the validation. So it depends how you want to perform the model. The point is, when you want to get a good model, the training data should be more than validation and the testing. That's why the training data set, it is good if it is more than 60%. or at least 60%. If you have more than or equal to 60% for the training data, it may be enough. Okay, we call it enough for building the model. The holdout method, yeah, you can check on the Google Colab. We can use the model selection. We can use the train test split. In this case, I'm using the X and I'm using the Y, and then split based on the test size. So the test size, I specify 0.2, then it means 20% for the test size. And we will have X train, Y train. This is for the training data. And I have the X test and Y test. This is for the testing data. If you want to apply again splitting into 3 sets, which is training, validation, and testing, then you can do again for the train test split, which is from the X train and the Y train. The result from here, X train, you want to split it again into sub data of the training, and we have the X for the validation. We can also do the Y train, which is the Y training or the sub data for the training, and the Y for the validation. So if you look at the code, if you look at the code, okay, let me run this. Okay, I will explain later about the parameters. So we have the X train and Y train. So I want to split it into the validation and the subcategory of the training. So X train and Y train, I will split again into the sub of X train and the sub of Y train. And then I have another data, which is X validation, and I have Y validation. And let's suppose I have the model again. I'm going to do the modeling and let the n or the k equals to 3. It means I'm going to check from 3 nearest neighbor. By using this k equals to 3, I'm checking the model with the sub data of the training. And when I predict it into the X valid, I'm checking the error. In this case, I'm checking the MSE and the RMSE. So I'm checking the error between the Y valid and the predicted from this model. Okay, the model shows that we have the RMSE is 8.54. So 8.54. This quite high because we want to get nearby 0. The second part, after the holdout method, we have the cross validation. The cross validation, sometimes we call it as CV, k-fold cross validation. It is a resampling technique for evaluating the machine learning models by splitting a dataset into k equal size folds. It is to get a more reliable estimate of a model's performance and to reduce bias compared to the single train test split. if you look at these figures, okay, at the previous one, we have a data set and we just split into training and testing. So it is, we call it single train test split. So only one time. When you split one time training and the testing, it is still not fair. Because when you choose the data for the training, it is random. When you choose randomly, we do not know whether the data is good, whether the data is bad. Sometimes if you choose only a good data for the training, then the testing may be only bad data. When you do the testing, the result is bad. Or sometimes you put the data on the training side randomly, and the data on the training side is very bad. And the data on the testing is very good. When you perform the testing, because the model created by the bad data, you cannot get a good performance. In order to avoid this kind of problem, we have the k-fold cross-validation. So the data set, we will split into k. K is an integer number, and it is from 1 until n minus 1. Okay. Now, let's suppose we have k equals to 5. It means I will split the data into 5 times. When we do with the splitting number 1, okay, we split into 5. 1, 2, 3, 4, 5. So the data in the fold 1, fold 2, fold 3, fold 4, it will be for the training. And the data on the fold 5, it will be for the testing. After we do with this thing, we will get the error. We call it error 1. Maybe we use the MSE. Maybe we use the RMSE. Then we get the value. And then next, we will do the splitting, the second splitting. The same, the split number 1, we split into 5 different fold. 1, 2, 3, 4, 5. Now, this section will be for the testing, and the remaining will be for the training. Again, for split 3, we will use this fold for the testing, the remaining for the training. This is for the testing, this is for the training, this is for the testing, and this is for the training. For every split, we will get the error. Let's suppose this is error 1, this is error 2, this is error 3, this is error 4, this is error 5. Then we can get the average error. So the average error means the total error divided by k. K means the integer number, how many splitting you did. So in this case, if we split into 5 times, then we will divide with 5. Then the error 1 plus error 2 plus error 3 plus error 4 plus error 5, it will be divided by 5. So the cross validation, yeah, we can specify with one of the function in sklearn. We use the model selection, and we can calculate the score using the cross validation score. The CV score, we can get the cross validation score. We call the model, which is the KNN, and then we perform into the data. Using this cross validation, okay, we just put the X. So we don't need to split. We don't need to split the training and the testing. We don't need to split it. We just use the X and we just use the Y. It means we used all the data and we specify CV equals to 5. CV equals to 5 means we will do fold when k equals to 5, then we will make 5 segments of the data, and then let's calculate the score. The score that we want to get is the negative mean square error. So it is the negative MSE. After we get the MSE, because it is a negative, we can get the RMSE. The RMSE means the square root of the negative of the scores. So this is using the cross-validation approach. If you want to define more parameters, so you can use the k-fold. So in the sklearn, we have the k-fold. The k-fold means we will specify how many splits do you want. For example, I specify the kf. It is the object of the k-fold from this model. And I'm going to split 5 times. It means I will split into 5 segments of the data. And then shovel is true. Shovel is true means it is randomly segmented into fold 1, into fold 2, into fold 3, 4, and 5. And after we have this kf, we specify again the cross-validation score. So we have the model, which is k and n. We use the x, which is all the data. We use the y, which is all the data on the label. And the CV means the cross-validation. We use the kf. Kf means the cross-validation fold number specified with some parameters. And the scoring will be the same with the negative mean square error. If you want to get the RMSE, then you can get the square root of the negative of the CV scores. Okay, this is the previous one. We want to check the valid data, the validation data with the sub-training data. And after we have the model, after we check the model with the validation data, we want to check the model with the testing data. So this is the checking between the testing data and the predicted data. So this was the previous one. And this is the cross validation. Okay, we use the CV equals to 5. It means the k equals to 5. And we use the negative mean square error. The NP square root minus CV scores means we want to do multiplication by -1 before we do the square root, because this measure is negative. That's why we need to multiply with -1. Then you will get the cross validation RMSE score. Okay. The cross validation RMSE score, you can check this one. There are 5. Why there are 5? We have 1, 2, 3, 4, 5. So this is the error for the segment number 1 or fold number 1. This is the error for segment number 2 or fold number 2. This is the error for segment number 3 or fold number 3. This is the error number 4, and this is the error number 5. And then in order to check the overall errors, we can do min or check. The average of RMSE is the mean of this score. Then this is the mean of the RMSE. The same with the cross validation. Here using the K fold, okay, we specify how many splits do you want. In this case, I'm splitting 5, and then I do the shuffle equals to true. It is randomly splitting. All are the same. Okay. Yeah, we use the shuffle. Shuffle means it is randomly splitting into 5 segments, and we got this result. So you can see that if we don't shuffle it, we just make the segment based on data. The RMSE is 7.1. When we do the randomize for segmentation, we got the RMSE is lower, 5.0. So the performance is better when we do the shuffling or when we do the randomize. Okay, note that this error, the lower is the better. The other kind of performance improvement, we can use the adaptive parameter. The adaptive parameter, or usually we use the grid search. We call it the grid search cross validation. It is a kind of technique used in the machine learning for the hyperparameter tuning. Hyperparameter. So what does it mean? We will have parameter. The parameter means something that you need to specify for the algorithm to run. For example, if you use the KNN, okay, so in the KNN, you will have the parameters. For example, what is the algorithm that you want to use? How many leaf size? What is the metric? What is the metric parameters? What is the number of jobs? What is the number of neighbors? What is P and what is the weight? So this is the parameters. But we also have the hyperparameters. So what is hyperparameter? The hyperparameter means each of the value. Each of the value will have different value. Every algorithms have different parameters. And every parameters will have different values. For example, do you still remember the distance metric? How many distance metrics do we learn? At least we learn Manhattan distance. We learn Euclidean distance. We learn about cosine similarity. So there are 3. But actually there are still more, not only 3. If you look at the number of neighbors, so we set up the number of neighbors is 3. Actually, we can also set up not only 3, we can set up 4, we can set up 5, we can set up 6, we can set up 7, 8, and so on. Okay. It means the hyperparameter can be any values. Now the question is, what is the best value? If I'm using Minkowski, is it better than Manhattan? If I use Minkowski, yeah, is it better than Euclidean? Or is better than cosine similarity? If I use the n neighbors equals to 3, is it better than 4? Is it better than 5? Is it better than 6? Is it better than 7? Or is it better than 8? You do not know. Then we need to do the hyperparameter tuning. So this tuning means I will check all the possibilities. So I will check what are the metrics, what are the possible metrics. Then I will list up all the possible metrics, and I will list up, for example, now I'm using the metric only for this one and the neighbors. Okay, for the remaining you can check on the documentation. So I'm going to check, we will explore a predefined set of hyperparameter values to find the combination that yields the best performance for a given model. So each algorithm has its hyperparameter. Now we are doing only K and N, but later if you do with decision tree, if you use another kind of algorithms, they have their own parameters. So for example, below is the parameter for K and N. You can specify the model, which is K and N, and then get params. You will see the parameters of that algorithm. Now, using the grid search, we have the grid search CV. I'm going to set up the parameter. So the parameter means I want to check. Let's say now I'm using the nearest neighbor and neighbors. This is from the parameters. So this is from the parameters that we have and neighbors here. I'm not going to check only number 3, but I'm going to check also when k equals to 4, when k equals to 5, and when k equals to 7. And I want to know which one is the best one. We can show all the performance when k equals to 3, when k equals to 4, when k equals to 5, when k equals to 7. And then the grid search, okay, we will do the grid search cross-validation. And I'm going to use the model K and N. And the parameter that I'm going to apply for the search is using the parameter grid. I'm using the cross-validation 5 times. So it means the data will be split into 5 segments. And the scoring, I'm using the negative mean square error. After that, I'm going to fit it into the data. So the data is the X and the label is on Y. Let's see. If I do this one, okay, we can get the best parameters. Okay. How to get the best parameters? You will need to get the variable best params. So the variable best params means after doing the experiment with 3, 4, 5, and 7, you will get the best parameters. And the best RMSE, it will be on the variable best score. Because the RMSE, the MSE, it will be the negative mean square error. So you need to put negative in order to make it positive, and you can do the square root. Then when you run this, you can get, okay, this is the best parameters for the nearest, the parameters is 3 at the original model. And the best parameters when the nearest neighbor is 4. Okay. So it means my assumption when k equals to 3, it is not model. Best model, after the hyperparameter tuning, we got the nearest neighbor equals to 4. And the best RMSE is 7.8 7. Okay, in this case, this model with the n neighbors 4 is better than n neighbors equal to 3. This one, the performance is not good, and this will be the best performance because the error is lower than the n neighbors equals to 3. The next, we can set different kind of parameters. For example, yeah, the metric that I want to use, not only the nearest neighbors 3, 4, 5, 7, but I'm also trying to make different kind of metric. For example, I'm using the Minkowski. Yeah, you can specify the Euclidean, cosine. Okay. Now the question is, how do we know this parameter value? So you need to check on the documentation of the algorithm. Okay. So in this case, you can go finding the KNN parameter using the scalar. A good library, they will provide this kind of information. This is the parameter nearest neighbor equals to 5. So if you don't specify the nearest neighbor value, the basic default value is 5. And the weights, when you do not specify any weights, then it is automatically designed as uniform, and so on. Okay. So yeah, you can have the metric. The default is Minkowski. So the Minkowski is using the p equals to 2, which is the Euclidean distance. If you want to use different kind of things, yeah, you can see the documentation. So there is also another kind of distance measure. Then you need to extract this information to make the hyperparameter tuning. This task is something you need to explore more. I cannot give you all the things. Okay? You can explore by yourself whether the value is possible for this metric or not. So for example, in this case, it is possible. With the Minkowski p equals to 2, actually, it is the same with the Euclidean. Okay. But this is just for example. And then we have another distance, which is cosine. After we have the n neighbors, and after we define the metric, again, we can call the grid search, and then we call the model KNN, put the parameter grid, the cross validation 5 times. So it means we will do the segment until 5 segments, and the scoring is using the negative mean square error. Now let's fit it into the data with X and Y. If you do this one, okay, the best parameter is the metric is Minkowski, and the nearest neighbor is 4, and the RMSE is 7.8. It means the cosine similarity does not give a better result. So the Minkowski is still the best among the other option of the metric. Yeah, you can explore your own. For example, as I mentioned to you, each algorithm has its own parameters. To find the optimal hyperparameters, we need to understand the parameters, and you need to explore the parameters in the official website. Let's say I want to know the parameters on the SVR. SVR is from the sport vector regression. then you can go to the link regarded with the SVR. So I give you the link here. And you can use this one. Let's say I'm going to check what are the parameters in the SVR. So you can see the SVR has kernel, degree, gamma, coefficient, total, and so on. If you want to expert in the machine learning, then you need to understand each of this parameter. In order to make a good workflow on the machine learning, we can use pipeline. Pipeline is one of the library in sklearn. It allows you to sequentially apply a list of transformers. So transformer means it is to transform the data before we do the machine learning, to pre-process the data and until conclude the sequence with a final predictor for the predictive modeling. We can use pipeline, which is from the sklearn pipeline. And for example, when you do the pre-processing, you learn about the standard scalar. You learn about the min-max scalar. Okay? So you use this scalar on your mid-exam data. And we use the pipeline to define. I'm going to use the scalar, min-max scalar, and I'm going to use the model KNN, which is the K nearest neighbor regression. So if you look at this flow, it means I'm using the KNN pipeline. The pipeline will automatically do this min-max scalar on your data, and then it will run the KNN as the modeling. You can see the pipeline is like this one. It is a flow. From your data, you can do automatically the min-max scalar. You can do automatically with the model, which is KNN, and you can get the result. So you can just call one time KNN pipeline. What is KNN pipeline? The KNN pipeline refers to this one. So you don't need to make every line. You don't need to make the min-max scalar line. You don't need to call this KNN regression. You just need to make this pipeline. Once you have this pipeline, then sklearn will understand. You will use this pipeline to fit the training data, and then you can do the prediction based on the pipeline, and you can do the prediction, and you can measure the performance using the mean square error. And you want to get the RMSE by checking the square root of the MSE pipeline. So using pipeline, actually it is more simple, but you need to understand what kind of pre-processing that you want to apply. If you already understand the pre-processing schema, yeah, you can just apply like this one, minimum, maximum scalar, and the K nearest neighbor. Then you can have a simple code to run your machine learning. Okay, let me stop. Okay, let's have a break. So during